Hello everyone and welcome back to my channel. Today I'm going to be showing you a video about integration. It's one of those maths tutorial ones that it's kind of pretty difficult. I've actually got my rubber. So yeah, integration is the reverse of differentiation. Differentiation is that one where you have like y equals something and then you do dy by dx and you get something else. So I don't have a video on that yet, but there will be one at some point probably. So yeah, integration, the one with this weird symbol, it looks a bit like an S, it looks maybe like an F, you decide. But yes, integration, let's start into the video. So what is the process of integration? We start out with x squared. How do we integrate x squared? So we do this, and we're integrating with respect. That just means like because there is an x in the formula, say. So yeah, I'll give you examples where it's not x, but it's pretty easy to work out what that means. So we are integrating x squared with respect to x. So what do? We raise the power by 1. So this goes to x cubed, and we divide by our new power. And then there's always something you have to remember. In integration, with this thing, you always put a c after it. There's usually a mark for writing c. So you get like 1 mark for doing this, and 1 mark for doing this. If you got something that simple to do in your exam, unlikely though, because the examples get a lot harder. Now this is in GCSE further maths as well, and also AS maths. So it's very handy to know. So let's do another one. Let's integrate 2p cubed. So we're going to integrate 2p cubed with relation to p, because there's a p in the equation. So what we're going to do is we're going to raise the power by 1, 2p, 4, and divide by our new power, 4. Remember to add c, and then do any simplification if necessary. So obviously this can be simplified to p to the power 4 over 2 plus c. So those are the very simple options. Now we can get on to some of the harder bits. So if we have, there's our integration sign. If we have x to the power of minus 2 with relation to x, what do? So we raise the power by 1, minus 2 plus 1 is minus 1. And then we divide by our new power, add c, and simplify, so we get minus x to the minus 1 over 1, so that can just go there. Or what you can write that as, minus 1 over x. So there's a negative example. Let's do another negative example. If we're going to integrate 2 over 3x to the 4 with relation to x, what we're going to have to do is we're going to have to write this in a form that we're comfortable with using. So we write 2x to the minus 4, because it's underneath, over 3 dot dx. Then we're going to raise the power by 1, minus 3 over 3. But we also have to multiply down by minus 3. Then we add c, and we get 2, remember you can bring that down if you want, minus 2 over 9x cubed plus c. You always have to remember the plus c. So that is how to do that. Now if you get fractional powers, things can become a little bit more tricky. For example, x to the power of a half. And then if you do background noise, just because my parents are talking in the background about I don't even know what. Anyway, yes, we're going to raise the power by 1. We're going to divide by the new power. We're going to add c. Now, x to the power of 3 over 2 divided by 3 over 2. This is the same as x or 3 over 2 divided by 3 over 2. Or we can rewrite divided by 3 over 2 as multiplied by 2 over 3. So then this goes to 2x 3 over 2 over, no it does not, does it? Yeah, it does, over 3. Plus c, because you always have to remember your plus c. So, those are the basic examples. Things to remember. Root x equals x to the power of a half. Cube root x is x to the power of a third, etc., etc. Okay. So now, what do you actually, what is this actually used for? Well, if you know the gradient function, as most of you should know, is dy by dx, and you know an x coordinate and a y coordinate, you can work out your original equation. So that, yes, you can work out the original equation from this by using integration. So let's give one of these a go. Now, by the way, if I may make mistakes here, please correct me in the comments if I get something completely wrong. Okay, so dy by dx, our gradient function, is equal to 3x squared plus 1. And then we have a coordinate, so our x value is 2 and our y value is 12. Obviously we can write that as 2, 12. That is our coordinate. So first of all, we're going to integrate this with respect to x, and we get 3x cubed over 3 plus 1 is to the power of 1. But we're not looking at the 1, we're actually looking at the x, and there's 1, which is actually x to the power of 0. We're going to raise that to the power of 1, and you get x to the power of 1. That does not exist there. But you get x, and we can simplify this by rubbing out the 3 and rubbing out the 3. And you get x cubed plus x, but don't forget your plus c. This is going to be very handy in a minute. So we have an x coordinate and a y coordinate, and we want to work out what y equals. So if this equation is our function of y, and so, or our function of y equals x cubed plus x plus c. We have here an x and y coordinate, so we can sub that in. 12 equals x, we have x, I keep doing this. 12 equals 2 cubed plus 2 plus c. 12 equals 2 cubed is 8 plus 2. 12 equals 10 plus c, therefore c equals 2. So our original equation that got us this gradient function with these coordinates is y equals x cubed plus x plus 2. And obviously if you were to differentiate that, you would get, bring that to the front. So I'll use this notation, y dash equals 3x squared plus 1. Full stop. Okay, so another use of integration, now this is probably the most useful thing, is say I have a curve. Here's a curve, we'll call it 1 plus x squared equals y. That is what this curve is. If we want to find the area underneath the curve, obviously, if it was a nice simple shape, like say it was just a line, here's our line, and we want to find this area, it'd be very simple because you just have to, length times height gives you the area of that rectangle. But with a curve, it's not that simple. Like, what if we wanted to find this area here, in here, and this was the point 0, this is the point, and that's 2. What if we wanted to find that area? How would you do that? Integration, because integration is great like that. So what we want to do is we're going to integrate our curve. Our curve is 1 plus x squared with relation to dx, but instead of just integrating that, we're going to put in our 0, because that's 0, lower number there, and our 2, because that's our bigger number. Then the notation changes slightly. We have some nice square brackets here. 1 becomes x. X squared becomes x cubed divided by the new power over 3. And we need to remember to put the 2 and the 0 there. Where's the plus c? Well, you could put a plus c in there, but you'll find in a minute why that is not necessary. So our next step is to put the 2 in and put the 0 in. So step 1, put the 2 in. We get 2 plus 2 cubed over 3. And we're going to take away, so we're going to have 0 plus 0 cubed over 3. Now obviously this all cancels out, but if we had our plus c's in here, that would be plus c minus plus c, and the plus c's will cancel, but however we have 0 in this, so we can just remove that. So now it's time to just work out what this bracket is equal to. This equals to 2 plus 2 cubed is 8 over 3, so it's 2 plus 8 thirds, which is, can I do the maths? 14 over 3, which is also equal to 4 2/3. So how do we check this? How can we know if we're right? Well, some calculators will be able to do that. So I'm going to integrate 1 plus x squared between the ranges of 0 and 2. 14 over 3, 4 2/3. And that's how you know we're right. So yes, we can find the area under a curve, which probably not something you ever thought you'd have to do before, but there we go. Finding the area under a curve. So we've got, let's do another example, because you know those can be pretty difficult sometimes. Let's do, yes, this one looks pretty interesting. So here's our, I'll do a nice small diagram here. Exciting curve. We want to find this area here. The question could ask, work out the shaded area, or work out the area between the curve and the x-axis. So that is the area that's like stuck, if you know what I mean. This area isn't stuck because there's still space, but this area is like stuck inside there. And our graph function is x squared minus 2x. Now, they could leave it like that, and you're going to know that that is 0, but you don't know what that is, or they could tell you. But it's pretty easy to work out if you just solve that equation. X squared minus 2x is y, x squared equals 2x, x equals 0, x equals 2. You'll know that that is 2. So we are going to integrate, and our things are 0 and 2. The curve is x squared minus 2x dot dx. Integrating that, we get x cubed over 3 minus 2x squared over 2, but of course that can cancel out with that. Remember plus c, but in this case it's not needed because we are doing definite integration, because there's numbers and you take the 2 c's away from it, you take a c away from a c and you get 0 c's. So we're going to substitute in 2. Remember there's a 0 here. We don't need to substitute in 0 because it would just mean the whole bracket equals 0. So we get 2 cubed over 3 minus 2 squared, which is equal to 8 thirds minus 4. Can I do that in my head? Probably, but you know what? It's quicker in the calculator. So we get minus 4 thirds, and you may be thinking, well, that's a bit strange. Why is our area negative? Like, why is that negative? Well, if you look at this curve here, you'll see that the area is underneath, it's in the negative y-axis. Y is negative in all that bit there, and our answer is negative, but it's an area, so the area is just 4 thirds. But if your area that you're working out is underneath the axis, you're going to want to make sure your answer ends up being negative, and then you just switch it to the positive one and you get the correct answer of 4 thirds. Now, if you don't believe me, let's use the calculator to check. X squared minus 2x between 0 and 2. Minus 4 thirds, but the area is obviously 4 thirds. Okay, so that all seems pretty easy so far. But it gets harder, because of course it does. This is maths. Let me see. This next bit I'm going on to is not in... let me check. That's the same question. Ah, here we go. This is not in GCSE further maths. This is just A-level maths. So if you are doing GCSE further maths, you can leave now. So GCSE FUMA has been done. Now onto the AS maths. All that stuff had been done in GCSE, so now the extra stuff. Okay, so let's look at one of the A-level examples. Let's look at this graph here. So we want to find the area under this graph. It tells us that is 1, that is 0, that is 3, and the curve is y equals root x plus 1. So you might be tempted to go, okay, so that's x plus 1 all to the power of a half. And then realize, how do you actually integrate that? Like, that is pretty difficult to integrate. In fact, you do that at A2 maths, and you don't learn how to do that till A2. So how do we do that with our AS minds? Well, look at this. So we have this box here. We could work out the area of this box and take away, and then we could also work out the area of this bit here and then take that away, because that bit may have a simple equation. Well, what is that equation? And how do we get it? Well, this point, this coordinate here, is whenever x is 3. So 3 plus 1 is 4. It's under the root and you get 2. This is 2. Nice and simple. So how do we work out this equation? Well, that is the y version of this equation here. So let's do that. If we square both sides, we get y squared equals x plus 1, y squared minus 1 equals x. Now in terms of x, we can now integrate this. Integrating between 1 and 2, y squared minus 1 dot dy, because y is in the formula. This gives us y cubed over 3 minus x between 2 and 1. So let's substitute in. We get 2 cubed over 3 minus 2 minus 1/3 minus 1. So if we use a calculator to work that out, that's 2 cubed divided by 3 minus 2. We get 2/3. Take away 1/3 minus 1 is minus 2/3, which gives us 4/3. So this red area here is equal to 4/3. That's great. So now what do we do? Well, we take it away from the entire area. 2 times 3 equals 6. Probably that line down there. 2 times 3 is 6. 6 minus 4/3 equals 14 over 3. Now, my calculator, who's obviously a lot smarter than I am, I put this in, and I put in the original equation, square root of x plus 1 between 0 and 3. Remember, this is that original one. We get 14 over 3. Therefore, this is our correct area under that awkward curve. So now, there's only one thing left to do, actually. That is on the A level. Oh, there's something loud passing. It is the area between a curve and a line. Now you may see some past papers which have an area between a curve and a curve. Those have been taken off. So we have the curve y equals x squared minus 2x plus 3. We also have the line y equals 9 minus x. And apparently they meet at points A and B, which is great, because we have 2 points. Find the coordinates of A and B. What do? This is a simultaneous equation, one linear, one quadratic. So x squared minus 2x plus 3 is equal to 9 minus x. X squared, bring that x over, you get minus 1x, because 2x minus x is minus 1. Plus 3 minus 9 is minus 6. is equal to 0. Now, time to factorize. And we get, let me see, if we have a 2 and a 3, and it's minus 3 plus 2, x equals 3, x equals 2. Now we want to find the coordinates of a and b, so 9 minus 3 is 6. 9 minus 2, 9, 8, 7. Those are coordinates of a and b, so we'll call this a, we'll call this b. Great. We've done the first part of the question. Now sketch the line and the curve in the same set of axes. So at this point you're going, okay, yeah. So yes, x squared minus 2x plus 3. Do you know what we're going to do? Well, I suppose if we put in x is equal to 0, y is equal to 3. And if we put in x is equal to 1, this is another way to sketch the curves. 1 squared minus 2 times 1 plus 3, you get 2. So when x is 1, remember this is 3. 2, we have this one here, we have this one here. If this is equal to 2, we get 3. And yeah, so then this curve looks like this. Then what, the line y minus x, well, we know it crosses at 3, 6, and we also know it crosses at 2, 7. Sorry, that should be minus 2. That was such a stupid mistake. So that is a minus 2. Yeah, that should be minus 2. Ugh, I'm so stupid. Right, so 9 minus minus 2 is 11. So whenever minus 2, we have 11. So you know that this line goes through those points. So we can sketch that there. So now it says, calculate the area of the finite region between the line and the curve. So the finite region is the wee stuck bit in here. So as we can see, this point here is 3, is here, is minus 2. Could we work that out? So how do we work this out? Well, we have this area under the line here, this parallelogram, no, not parallelogram, it's trapezium, underneath this line, and then we have the normal integration here. So what we could do is we could work out the area under this curve, this red one here, work out this area under that curve, and take it away from the area underneath the line. We'll get that bit there. So let's do that. So let me clear this a bit. So remember, we're working out the area under the line. So you can either integrate this or just actually use your formula, a half AB, half AB H, half A plus BH, that's what it is. But, let's integrate. So we're integrating between minus 2 and 3. 9 minus x dot dx, you get 9x minus x squared over 2 between 3 and minus 2. And you know what I'm going to do? I'm just going to type it in my calculator, get it all done in one go. So this is 9, x is 3, minus 3 squared over 2. So this is, so yeah, this is 45 over 2. And we're going to take away whenever x is equal to minus 2. Minus 20. And so our area is 45 over 2 minus 20, 85 over 2. Can we confirm that? So we have 3, 4, 5 as our height. We also multiply that by half, and then our things, we have 11 is what we worked out there, plus 6 is what we worked out there. 85/2, so that is our area under there, done both ways. Okay, so now for the area under the curve. So we're integrating between -2 and 3, the curve x squared minus 2x plus 3 dot dx. Because there's an x in the equation, you get x cubed over 3, 2x squared over 2, but remember, because it's 2x squared over 2, you can cancel out the 2's, plus 3x. 3 and minus 2, so obviously I'm just going to type that into my calculator again because there's a lot of working out to do in this page. So whenever x is 3, we get 3 cubed over 3, which is the same as 3 squared, minus 3 squared, plus 3, there's another 3 squared, and you get 9. We're going to take away whenever x is equal to minus 2. And that is minus 38 over 3. 9 minus 38 over 3. 65 over 3. And so our final thing is to take this answer here away from this, or take that away from that. 85 over 2 minus 65 over 3 gives us 125 over 6. That might look like a really stupid area and you can't do it immediately in calculator, but I'm going to check. So it's area under line minus area under curve. (125/6). Therefore, we get the correct answer. So yes, this is probably a very long video on integration, but please, I hope you enjoyed it. Let's draw one of these people. Hope you enjoyed it. Make sure you hit that thumbs up button. You know I can't draw. And also hit that subscribe button, because by the way, we hit 300 today. Or this morning I woke up and we were on 300. So, I mean, happy 300. Subscriber special will be coming soon. Promise. But yes, thank you all for watching and I'll see you all next time. Bye.